Welcome to everyone. This short presentation of our model about the diffusion of the virus, creating the COVID-19 pandemic, is mainly related to the possibility of inspiring interventions, policies of interventions via modeling capabilities. Our model is inspired to SIR model with infected, separated between symptomatic and asymptomatic agent, susceptible agents, and recovered agents. Being an agent-based model, we can micro-simulate the places where the contagion occurs and micro-simulate the transmission of the contagion between the agent transferring the disease and the agent potentially receiving it, looking at the characteristic to both the component transmitting and receiving. The model is built upon structural data of Piedmont, but can be adapted to other areas. It uses a realistic calendar via a script interpreter. It is online at this address, where it is possible to find infos on the construction, a draft of a paper reporting result, and run directly the code via an executable version of NetLogo in its web version. The model is able to produce sequences of contagions that we can analyze. We represent infected agent as horizontal segments, starting when the infection of the agent begins and finishing when the infection of the agent finishes. The horizontal axis, the x-axis, is devoted to the time. Each infected agent is a segment at an upper level, and vertical links join the infecting and the infected agent, with colors related to the place where the infection occurs, thickness related to the fragility or robustness of the agent, the style of the segment with a dotted line for the incubation phase, a dashed line for a symptomatic agent, and a solid one for symptomatic agent. We display multiple data together and we created the possibility of understanding at a glance how an epidemic episode is spreading. In this way, it is easier to reason about countermeasures and to develop intervention policies. Here we have an inspiring example. Let me start from the left-right corner, where this plot clearly show how the representation of the agent by segments work. As an example, this is an agent infected at home and there's showed a cyan color, and it is infecting another agent in the workplace, so the brown color. Both these and these are asymptomatic agents, so represented by dashed segments, and this is the dotted part of the incubation phase. Let me go back and start examining the picture on the top left corner. This is a huge epidemic with a very important part where the contagion occur in workplaces involving a lot of fragile people represented by thick segments. What can we do? We can stop fragile people, sending them home with a sick pay, relevant sick pay, and the effect is evident. Here in the first part of the top right picture, we have an epidemic without contagions, and the conditions are the same at the beginning of the previous case. But in this case, a single person, we can see it, she or her, but is an agent, so it, in this enlarged copy of the picture, an agent infected at all, cyan, is the unique continuator, is the bridge to another agent in a workplace, so brown, restarting the second wave of the infection. What we can do? We can stop all fragile people of any kind, both workers, aged people, people in nursing homes, people in hospitals, and so on. And the effect is this one, simulation of very short duration with a limited number of infected agents. This is always the same starting point. This example is very inspiring, but it is a flash. We have to work in a more systematic way. So we introduce batches of simulation. We run 1,000 times the same model, changing only the random seeds, but keeping firmly the same rules of control of the simulation. And in these batches, each epidemic, each run is an epidemic, is a point in a space with, on the x-axis, the duration, the time, and on the y-axis, the number of cases of contagion, both symptomatic and asymptomatic, and also the diseased people. Then we represent these batches, I repeat, of 1,000 repetitions of the model, both with the usual statistical indicators and adopting the technique of the heat maps. A heat maps is a double histogram creating cells. In each cell, we have the cases with that duration and that number of infected people. And here you have two dramatically different cases. On the left, the even of negationists. Here, we suppose that we do not have any kind of intervention. Anyone is free to do what it wants, is an agent, it. We have very few cases of epidemic with short duration in the bottom left corner, and a cloud, terrifying cloud of epidemic lasting more than 1 year, 1.5 years, with from 2 millions to 3 millions of contagions in a region like Piedmont, which has 4,350,000 people. On the contrary, on the right, we adopted the non-pharmaceutical containment measure of the Italian government and of the Piedmont regional government, and the effect is to concentrate on the bottom left corner the majority of the events, sure, with the spread, because this phenomenon can start on the basis of a thin events like we saw in the previous slide. Where is Piedmont here? It is in this cell because the duration of the epidemic in Piedmont that at the end of May started to have a flattened curve of contagions, symptomatic contagions, has been close to this length, little bit less, with 30,000 symptomatic cases in the scale of the model. To have the total, we have to multiply by 3. So we are in this cell, just on the right of the mode of the distribution. What kind of intervention we can plan? We start with no control, disaster, both as number of symptomatic or total infected and as duration. The mean is 1 year. We move to regular non-pharmaceutical intervention of containment with a huge gain. Also opening school in September, and the results are a bit better as number of infections, and the explanation is that keeping part of the young people constrained in a safe place as the school where no external contagion can meet the person inside the school, visitors are not allowed, we have a little improvement over the results. But a very strong improvement is that of keeping fragile workers at home, remember, always with the sick pay. If we stop also all the fragile people, the result is absolutely better. In this case, we can also decide to have all the factories, shops, offices, workplaces open in all the duration of the epidemic. The result is not so bad, and the cost-benefit analysis, putting on one side the cost of stopping the economy, on the other side the cost of paying sick pay, relevant sick pay, is absolutely in favor of this second option. Here, if we open a school, we have the same difference that we saw before, and the result is absolutely optimistic and positive. Just to have a final consideration, the organizer of the meeting where this slide has been presented in September 2020 asked this question to the participant, and our reply about what the model speaks about is that the model is able in comparative analysis, not forecasting, because we have at the base of anything a very huge intrinsic standard deviation of the phenomenon, variance of the phenomenon. The model can be easily adapted to different epidemics, can start very quickly in a new crisis because it is hugely parametric, and most of all, it will be in the second version that we plan to build in Python using this shell, which is a creation of mine, a free open source shell. Many thanks for your kind attention.